The world of construction management, where you have to learn how to do everybody's job.
Do your job! Do your job! Do your job!
Essentially, no matter how much I sit here and yell,
"This isn't my job!"
I still have to do it, and so does everyone else. And so, may I present to you our domestic shed project. Now, let my absolutely non-mathematical brain just try to tell you how it all went down.
Right, so the first part of the assignment, we had to determine wind loads and design the girts and purlins. We gave our building the location of 333 Macleod Street, Cairns, North Queensland, with the building design parameters as follows. And no, my screen is not dirty, it's scratched, okay? It's scratched. So, while I wrote a fantastic, riveting introduction that would make Shakespeare quake, the smart ones were off calculating the self-weight of purlins, the weight of the ceiling, weight of insulation, services, and loads. The focus of this assignment is to design a basic shed in a Region B location, in accordance with Australian codes and regulations, while demonstrating critical thinking abilities in terms of design, problem solving, and identifying various hazards. The proposed shed will span 6 metres, reach 5.6 metres in height, and is classified under Wind Terrain Category 3. When designing a shed, a multitude of structural elements must be taken into consideration in order to produce a fully functioning, safe and practical construction, which will remain fit for use and be durable enough to lessen the need for maintenance. Fundamentals to consider include bracing layout and design of bracing elements, purlins, typical sidewall girts, columns, rafters and design loads. The shed will be designed as a braced box structure, an effective design in terms of wind loads. All connections will be pin ends made from structural steel, as this is the most successful option in terms of withstanding tension and compression. The roof and walls of the proposed shed will be Lysol trim deck, a superlative option in terms of shed design, as the long-spanning cladding allows for wider spacing between supports. The purlin and girt sections will too be made of Lysol manufacture. Determining design loads, such as dead and live loads, is crucial to the process in order for the shed to be able to support and sustain loads and resist forces. Wind loads must also be taken into consideration. Wind actions occur when airflow applies pressure on a windward wall, passes over a structure and moves away from the surface of the roof, creating suction, and therefore creating suction on the leeward wall also. Failure to calculate wind loads appropriately renders the structure susceptible to damage and negatively impacts the dynamic quality of the structure. The proposed shed in this scenario is located in Region B, with no shielding and a wind terrain rating of 3. Now, 2 words. Roof bracing. In order to design the roof bracing, all compression and tension forces need to be calculated. These have been calculated through the use of method of section and method of joint, as well as the R-loads have been found. The diagonal members and struts were calculated as you are seeing on screen right now. The bracing member chosen for diagonal member 1 is a rectangular hollow section, 65 by 35 by 2.5. Lot of numbers. This member is safe for bending at both X and Y axes, as their load capacity is higher than that of the design force being 11.21 kN. For this member, we were designing the critical load, which in this case is compression. The bracing member chosen for strut member 1 is a square hollow section, 65 by 65 by 3. More numbers. This member is safe for bending at both X and Y axes, as their load capacity is higher than that of the design force being 20.96 kilonewtons. The bracing member chosen for strut member 2 is a square hollow section, 35 by 35 by 1.6. This member is safe for bending at both X and Y axes as their load capacity is higher than that of the force being 1.74 kilonewton. In this case, the table stops at length of 5 meters and the length required is 6 meters. The table has been manually extended and assumed as to the direction of the member line. When designing the wall bracing, what needs to be considered is the horizontal roof truss is supported by the vertical truss, the wall trusses, or the vertical bracing are the supports of the horizontal bracing, hence the reaction of the horizontal truss is the lateral load for vertical bracings. I hope that made sense. In this case, it is assumed that the wall bracing is long and slender, and that compressive members are assumed to be zero force members, and all panel shear is resisted by tensile diagonal only. Members under compression force are ignored. Equal angles are used as tension cross bracing, and the forces are relatively small. All members designed check out with all serviceability requirements and fitted within the capacity table parameters. Firstly, we had to calculate the loads and then the load combinations. The next step was to design the purlins. The fourth step we took is to determine the unrestrained length and then use the capacity tables to select the member that correlates to the maximum unrestrained length. After that, we calculated the reversal actions, to which we found out that no fly bracing was required. We then calculated the serviceability limit state. The rafter was deemed unsafe, and so we had to repeat steps 5 to 8, selecting the member from the capacity table to calculating the serviceability limit state. The final member selected was member 150UB 18.0. Now to column design, where at the last minute, we found out that we had calculated them all wrong and had to redo them. This assignment truly felt like we were going around and around and around. To design a column, we first calculated the loads and load combinations. Using the load combinations, we were able to find N maximum and MX corresponding, and vice versa, MX maximum and N corresponding. We calculated the buckling in and buckling out plan. We then used the capacity tables to find a suitable member, which turned out to be 150 UC30. We then checked if the member was suitable for buckling in and buckling out. We checked the column capacity for the combination of compression and bending moment to make sure it is safe, and hooray! 150 UC30 was the member of our dreams all along. In terms of space gas...
Hey, you can do the space gas stuff, right? Nah, bro, I thought you knew how to use space gas. Dude, I have no idea how to use space gas. I didn't touch it at all last year. So what are we gonna do? That's a tomorrow problem. It's due tomorrow. It's a tomorrow problem! And so, after finally knuckling down, we finished our shed. Yeah, so for the purpose of our assignment, we have a nice shed right here. It's not quite the one we built, doesn't quite look like the one in our assignment, but it's a shed. We out. Begin! We're recording?
Yeah.
Cool, alright. Yep, so that worked well. Alright, let me think about what I'm gonna say first and then I'll do it. Alright, we can stop recording for a second. Alright.
This is the
It's
behind
not
the
quite
scenes.
the shed that we built, but it's a shed. And for the purpose of this assignment, for purpose of context, we've got our shed. And then I'm gonna walk off, and that's how I'm gonna do it.
Go.
Hey, you can do the space gas stuff, right? I'm not gonna put that in. Do your job! Feel like a construction manager already. We can cut now.
No.
We can cut.
No.
It's enough.
Nah.
It's enough. Stop it.